Okay, here's another example of an application that leads to a system of linear equations. The first example is balancing masses. In some ways, this is balancing atoms, right? This is a chemical equation. So you see these complicated chemical formulas. I don't even want to try to pronounce this, toluene. I don't know, you guys probably, some of you chemists probably know better than me. But you have these two molecules are input into a reaction, and then they output these other two molecules. One of those is water, that one I can say. And you want to know the values of the variables, right? Like the coefficients to put to make the equation balance. So if you've taken any chemistry at all, you've done this, and you might know a chemistry approach to it. I want to do a mathematical approach. And so one way to think about this maybe is that like for each atom, like carbon atoms are involved in this, right? So you could, for example, think that like the number of carbons going in have to equal the number of carbons going out. Right, and if you do that, if you think about that, you could sort of start to write an equation from that. And you might pause the video and think about what the equation is going to be. How many carbons are going in terms of X and Y, and how many carbons are going out in terms of Z and W. So pause the video, try to write the equation down, and then I'll write it down. Okay, I see, so since it's C7 in the first molecule, there's 7 carbon atoms there. So if you have X of those, there's going to be 7X carbons from that first molecule. There are no carbons in the nitric acid. And so I guess you could almost say 0Y if you wanted to. And then I see 7 carbons in the first molecule in the output. So that's 7Z, right? And then again, there's no carbons in water, so you get something like that. Okay, so you get an equation from that. Again, pause and try to do the same thing for hydrogen, nitrogen, and oxygen. Try to write down the equations you'll get. So if we go about that, I'm just going to put notes here for hydrogen, nitrogen, and oxygen. If we do that, so let's see, this just means similar here. This is going to be more complicated because hydrogen's everywhere. We get 8X from the first molecule, really just 1Y, right? There's just one hydrogen that goes in, and then 5Z, 5Z plus 2W, right? And then similarly for nitrogen, I'll be a little quicker about this. I think we just get Y there, and then we get 3Z there. And then for oxygen, I get 3Y going in, and that's got to equal 6Z plus 1W going out, right? Okay, so now we have 4 equations and 4 variables. Again, this is a system of equations. 4 equations and 4 variables. Now, if you play around with this, you can see some stuff pretty quickly. So you might think about just like, again, if you wanted to just take the sort of down and dirty way to solve it, you might pause and take a minute to do that yourself, or at least get some relations among the variables. So pause for a minute, try to figure out how to simplify some of these. And if you do that, I think you end up with the following. I think you find out pretty quickly that X equals Z, and I think Y equals 3Z, and actually that ends up equaling W if you sort of plug in and simplify some stuff. And I think that actually works. So you could sort of say something like this is useful, although even this begs a question. It kind of shows you something, right? It kind of shows you can pick something for free. Like the variables are related to each other, but there's none of them equal, like, I haven't shown that x equals 7 or something like that, right? So, so I'm just gonna write this word, like there's a free, this is the term we're gonna use, as a free variable. Like say pick W or pick Z to be whatever, and then that forces X, Y, and W. Okay, so that's going to be the way we're going to look at this. But again, I want to do this in this more systematic way where we sort of really write everything down systematically and do some sort of steps. Again, this is supposed to illustrate a general process here. Lost my iPad for a second. It's supposed to illustrate a general process. So I wanted to be, again, super systematic. So let's rewrite this again like we did in the previous example. So I could write the first equation as 7x plus 0y minus 7z minus 0w equals 0. Somehow that does not look like a 0. Okay, the second equation, if I'm going to rewrite it, if I move everything to one side, 8x plus 1y minus 5z minus 2w equals 0. Third equation, there's no x's. There's 1y minus 3z if I pull it from the right, and no w's. And then the final one, no x's again. 3y minus 6z minus w equals 0. Okay, a couple things to notice here. We've got now all our 4 variables on the left, like it's that thing I did in the last example where it's like, look, all the x's are together, all the y's are together, all the z's are together, all the w's together, and actually all the constants are after the equal sign, and all the constants are 0, so that's kind of interesting. Turns out to be a special case that we're going to come up, that's going to come up a lot. And so we'll see that happening. Okay, I'm being super pedantic here, trying to painstakingly show you what's going on. Here are the system of equations that we have now, written in a more systematic way. Let me actually move this whole thing down over here. Fancy, right? Because I want to show you that there's something going on here. We have an array of numbers, and again, this class, it's going to end up being about matrices. And there's actually a way to rewrite this all. If I kind of want to just drop all the variables, the equal signs, the pluses and minuses, and just keep the numbers, right? So if I do that, if I just record the numbers, right, then the first line has a 7, 0, minus 7, and 0. And then I'm actually going to draw this vertical bar here to kind of really represent the equal sign, and then put another 0 so that represents that 0 is sort of that 0 right there, okay? Okay, so then if I copy the rest, do so at your leisure. That's a 3. Minus 6, minus 1, 0. Okay. There's a name for this. This, well, okay, there's a couple things. Just the 4x4 part is called, this is called a coefficient matrix. So it's the coefficients of the linear system. The whole thing, we do this whole thing, this is called an augmented matrix, because you augment with this extra column that gives you the constants that are after the equal sign. We could have drawn something like this for the 2x2 example, but I want to start bringing the matrix notation in, partially because it's less to write, right? It's just less to keep track of. But now I want to, okay, so that's the first thing. Now, the next thing I want to do is start thinking about the kind of steps we do here, right? So the first thing we would do here, oh, another thing I want to do actually before I move on, it's worth calling these, this is equation one, but since the matrices come in row and columns, we're going to call this row one, row two, row three, and row four. And I'm just gonna label these ones also, even though it's sort of really equation one, equation two, equation three, equation four. But okay, so if you think about it, I just kind of want to do it because we're going to refer to things in terms of the rows. So maybe a first step to do here would be to notice the sevens in the first row. We could just divide through by 7 to make things kind of nice, right? So one way you can write this is we'll take row 1 and we'll replace it with 1/7 of row 1. All right, and I can do the same thing here. Row 1 to 1/7 of row 1. All right, and if I do that and rewrite, and with on the equation on the left, I might drop the zeros just to keep my sanity, but in the matrix, I have to keep the zeros there. But so here we just get x, I'm just gonna leave some space, minus z equals 0. And I'm gonna copy all the rest, which is, again, something that gets kind of annoying here. But I'm trying to be painstaking in this example just to show you the general approach. Leave off the... Hopefully I'm copying things right. I wrote it on paper to check against. Okay, and then that actually changes the matrix if we sort of want to, again, this is a system of equations here, but if we want to compare to the matrix that we have, we basically turn the 7s into the first row into 1s. So we get 1, 0, minus 1, 0, 8, 1, minus 5, minus 2, and so on. You can speed up the video. You can change the video to 1.5 times or 2 times if you want at this point. But I like to kind of go slow and show everything so you can go through this as slow or as quickly as you want. All right, so that's the first step. And now what's the next step? Well, if you think about what we did last time with the mass balancing, it was really thinking, okay, we can get rid of this 8x right here, right? Because we could subtract 8 times the first row from the second to cancel out the 8x. And we can do something similar here. We can turn this 8 into a 0. That's sort of the corresponding thing that we would do, right? I guess just to make certain, these correspond directly to each other. I'm just kind of notating them differently, okay? So let's think about that. So the next step, okay, I'm saying, I know this is painstaking, but we'll get there. So the next step is I want to take row 2 and I want to replace it by row 2 minus 8 times row 1. That's kind of what we're doing. You know what? I'm gonna, so I don't have to write that twice. I'm gonna just put it here, move it over, and then that. Okay. So that'll clear out, that'll get rid of, like I said, that 8x. So if we do that, you can check my math. I might start going a little bit more quickly just to not bore everyone to tears. Or again, you could pause and do it yourself and then, you know, fast forward through and see if you get the same thing I get. So again, I'm going to copy, this is x minus z equals. So the first row didn't change, but the second row is going to change because we subtract the 8x, that the 8x goes away. The y is not changed because there's no y that's react. The minus 5z right here, we're subtracting 8 times negative 1. So if you think about it, there's a little kind of a, right down there, there's going to be a minus 5 minus 8 times negative 1. And so that's minus 5 plus 8 is actually plus 3. So that's the kind of computation we're going to do. So this becomes a plus 3z. And then this minus 2w also doesn't change, right? Okay. And then the third and fourth row don't change either. So, so actually, let me go over to the matrix here. So I'll just start this. So we get 1, 0, minus 1, 0, augmented with a 0. And then, like I said, this changes to a 0. That doesn't change. -5 minus -8 is -5 plus 8 is +3, -2, 0. Okay, so it's going to look like that. And then I'm just going to copy the other equations. This is the only time all semester I'll write these back. I'll write these side by side like this. It's just worth doing once, and you should try to do it once. Because at some point we're going to immediately convert to matrices, do everything in matrices, and then convert back to equations at the end. But I just want to show you how they work side by side. Okay, so let's see. This is 0, 1, -3. And this is 0, 3, -6, -1, 0. Okay, now what do we do next? Well, again, you see this, we've gotten rid of all the x's. We have this one x here, there's no x's below. Now we have this y. We can get rid of these two y's terms by subtracting the right things, right? So, and over here we have a 1 with all zeros below it, and I want to take this one and also put zeros below that. I wasn't sure if it was still registering. Okay. Doing this on an iPad, recording through Zoom, it's making sure it doesn't stop registering my iPad things. So, okay, sorry. So what we're gonna do now, just to kind of, same kind of thing, but we can actually write both steps down. So we're gonna take row 3 and we're gonna subtract row 2 from it. So I'm gonna replace that by row 3 minus row 2, right? That'll cancel the y's. And then we're gonna take row 4 and subtract 3 times row 2, because that'll do the 3y minus 3y, right? This 3y and then minus a 3y there. We'll cancel that out. Okay, so that's what we're gonna do there. And if we do it, here's what you should get. Maybe I'll talk less and just write. First and second row don't change. Third row, we get y minus y, that goes away. We get a -3 for that. Let's see, we get a -3 -3, so that's -6 actually. That's so, okay, I just wrote that for myself. So that's a -6z. And then we're actually subtracting the 2w, so we get a +2w here. And then we do something similar with the y's cancel, and then we get a -6z minus 3 times 3z. So that's -6 minus 9 is -15. Okay. So -15z there, and we get -w minus 3 times -2. So that's -1 plus 6 is +5w. I wrote that on paper and messed it up about 5 times myself before I got it right. So it's not, these are just, it's tedious, but okay. And so again, let's see, let's just make sure. So over here with the matrix, we get this. The first 2 rows don't change again. And then what do we get in the second row? So it's nice, we have zeros all down here, and now we have this -6 and this 2, and this -15 and this 5. Okay, and I just want to call attention to something. We're starting to get this nice pattern, and this is kind of, we have this sort of like staircase pattern that's starting to show up, right? And that's going to actually let us sort of find one, eventually get a variable isolated, find out its value, and then work our way back up. That's kind of the point here. That's what there's this algorithm that we're going to developing that I'm sort of trying to get at sort of naturally, which is it's called the row reduction algorithm, or there's another name, Gaussian elimination. I'll talk about it more next week. But that's going to be the idea here. That's the idea, is to get these staircase patterns. Okay, next. I'm going to try to make put a 1 right here in front of this z, because now it looks, we have a 1x here, we have a 1y here. It'd be nice to have a 1z there. And it's going to introduce fractions, but you know, we can handle fractions. So I'm going to take row 3 and I'm going to divide it by -6. So row 3 is going to actually, I'm going to, or maybe I'll multiply it by -1/6. Okay, so if we do that to both of these, all right, I know this is taking forever, I'm sorry, but we got to do one of these painstakingly. Pretty quickly, we'll start to ask computers to do it all for us. Again, we're not changing the first 2 rows anymore. So now, okay, that becomes z, and then we get -1/3, right? If we take 2 divided by 6 with a negative sign. And okay, and then in terms of the matrices, just trying to put parentheses around this just to say it's a system of equations. We have to do that. At some point, I'm gonna start to like to write these in columns. Now we have a 1 here, and we got a -15 here. 0, -2, 2, 5. Oh no, oh. I messed up. This is a -1/3 right here. And that's still a 5. Okay. Ooh, fun. Only about 17 more steps. No, I don't think so. Okay, so now it's kind of, you're starting to see the pattern. Now we're going to actually clear out this -15z and make this -15 into a 0. Okay, so we're going to do that by adding 15 times row 3 to row 4. So we're going to take row 4 and we're going to replace it by row 4 plus 15 times row 3. Right? Okay. We're copying. Now I'm just copying the first 3 rows. No typos, that goes away. We get 5w minus 15 times 1/3, which is 5. Yes, we get 0 equals 0. That's interesting. That's the first, okay, that's an interesting thing that just happened, right? We somehow got the whole 4th row to just completely go away. We actually really lost an equation now. We'll talk about the implications of that in a second. -1, 3, 1, 0, and 0, -2, -1/3, 0. Okay, this is fascinating because it turns out now we're kind of seeing what's going on here, which is like notice if we'd gotten w equals, if we'd had a w on the left over here, right? If we had a w, if we had like 2w equals 0, that would have told us w equals 0. And then going back all, oh my God, look how much I've, all the way back to these equations when w, if w was forced to be a specific value, then that would have forced x, y, and z. In fact, if w was 0, that would have forced x, y, and z to all be 0. Which you can sort of imagine, you can sort of trace back now when I get all the way down here. If w had been 0, if there had been a non-zero coefficient of w here, then that would have been 0, which made that 0. These both would have been 0, which would have made that 0. This would have been 0, which would have made that 0. So everything would have been 0. So actually, it's kind of cool that we got 0 equals 0. It sort of shows you that something interesting is going on here. At this point, you can just sort of start to make conclusions, right? You can now say, well, okay, z is 1/3 w. And then you could plug that in up here. You could plug 1/3 w in for that z and that z, and you could get x, y, and z in terms of w. Get x, y, z in terms of W, kind of like we did at the beginning, but you sort of start to see it this way. Again, I want to notice too, we also have this sort of staircase pattern. Notice actually it goes like that. This is going to be the goal, to get this sort of staircase pattern to make our lives really good. Just to really belabor the point, I'm going to actually go further, because now, so this, by the way, this is something, maybe I'll just go ahead and say this because this is, I'm previewing something important for later. These two things are called echelon form. Both the system and the matrix are in echelon form. It's just a terminology. And it's this staircase terminology. In fact, I think echelon, if you look up Google the definition of the word echelon, it says something about military formation where things form this sort of staircase pattern. So yeah, so that's echelon form. And then from echelon form, you can do this sort of what they call like back substitute. Once you know, well, you don't know W, but you know, we could get every variable in terms of at least one variable. Okay, so that is we could stop there, sort of solve. But I want to go further. There's actually another thing called reduced echelon form. And if you think about it, now that we've got the staircase pattern, we could actually use this Z to get rid of this Z and this Z, and actually even simplify things further and actually really explicitly get X, Y, and Z in terms of W in the equations. So I'm gonna actually do that step. So, and it's only one more step, I think, that we have to do. So, okay, so if I want to do that step, what I can do then is, in a very similar way as before, I can take row 2, and then I can, well, let's see what I want to do. I want to subtract 3 times row 3, because that will take this 3Z, and then I'll subtract a 3Z, and then I'll get rid of this 3Z. It'll go away. And I guess actually I should have, well, you know what? I should have set it for, let me move this down a little bit, because what I really, and then I want to do the same, something similar to row 1. Row 1, I just want to add row 3 to cancel out the Z, right? No, wait, this, sorry. That's supposed to be a minus sign right there. And this is supposed to be, there's a plus sign. So if I just add row 3 to row 1, then I think that should work out. that's the step I'm going to do to those. Let me draw these arrows a little better to illustrate what I'm trying to do. Just this red stuff's in the way now, but I'm going to take this and I'm going to go like I'm doing that. I'm just trying to go around this red stuff. Okay, so these are the operations I'm going to do. All right, so now rows 1 and 2 change, but if you think about it, let's see what happens to row 1. Okay, so again, you can pause it. You should be pausing frequently and trying to do stuff to get ahead of me. But I think what I get if I add row 1 and row 3, I think the new row 1 is this. And the new row 2, well, I'm going to do minus, so I'm going to do -2 minus 3 times -1/3 is +1. So I think it's minus, okay, so I think that's going to be Y minus W. And then the third row doesn't change, Z minus 1/3 W equals 0, and then this is 0 equals 0. So, and then the matrix is reflected, the same operations are reflected. If you just think about up here, like if we add these two together, and if we add these two together, right? If I do -1 + 1, I get 0, and if I do 0 + -1/3, I get -1/3. And so it's really, again, we're going to really want to look at this in the matrix way, because that's sort of the easier way to do it. So we get 0, 0, -1/3, 0. Here we get 0, 1. Similarly, we take this, we subtract 3 times that. We take this, we subtract 3 times that. -2 minus 3 times -1/3 is +1. So it's a -2 + 1 is a -1. Whew, I swear to God, we're almost done. And that's actually not where that goes. Sorry, that is a 0. and that's a -1. Okay, and then, okay, and now we're done. Oh, sorry, it's copying things. Okay. All right, and this has something even more stark. This not only has the staircase pattern, but it also, sort of, you've isolated X, Y, and Z in these nice, and you can really get it directly in terms of W. And over here, we have the staircase pattern, but we also have these three special ones that are kind of, you might even notice each of these columns just has all zeros and a 1. And then there's this kind of weird column at the end. I'm going to go ahead and tell you terminology because it's going to come up all the time. These things are called pivots. These are called pivot columns. And this is a free column. It's called free because there's no pivot in it. And I want to talk about what this means. How do we interpret this? But again, if we had something much more complicated, this would have been the way we had to go about it. The equations were sort of easy enough that we could have eyeballed some stuff and made some manipulations. But if the numbers were all crazy, this is something much more systematic. And I know this video is getting very long, but we're almost done, I promise. Okay, so, and hopefully this will be kind of the ugliest computation we do the whole semester. The second video, wonderful. Okay, so if we reinterpret this now, notice what we say. We can say X equals 1/3 W, Y equals W, Z equals 1/3 W. And then W is the 0 equals 0. Well, it's one thing you can do is you can just sort of say, well, W is just W. So the idea is that W is free. We can choose it to be whatever we want. Right? And if you do that, so for example, maybe a nice choice would be W equals 3 because of the 1/3. Then that would lead to X, Y, Z, W. We get this 4-tuple is really, let's see, X is 1, right? Because 1/3 of W, Y is 3, Z is 1, and W is 3. So going all the way back to the chemical equation, you basically need one of the first molecule, 3 of the second molecule. You put them together, you get out 1 of the third molecule, 3 of the fourth, which was water. So that's kind of the way to do it. Again, I know this is a very, very long way to do it, but the numbers were crazy. That's what you have to do. But you could pick something else. I mean, this, if you just think about mathematically, if you just think about this equation mathematically, I mean, if you wanted to have, 30 for W, then that would give you 10, 30, 10, 30, which, by the way, makes sense chemically, right? If you sort of always need a 3-to-1 ratio of the second molecule to the first. And as long as you have that, the reaction will happen. You'll get out a 3-to-1 ratio of the fourth molecule to the third, of water to the third. And I could even take things that don't make sense chemically. I could do W is minus 10 or something. And then you would get, what was it? Minus 10 thirds, minus 10, minus 10 thirds, minus 10. So my point is that this system has infinitely many solutions. They're in a nice form, and we can actually write the form down. But unlike the previous example that we had with the balancing of the masses, this has infinitely many solutions. It's not just because it's 4 by 4, it's because it's 4 by 4, but it had this extra thing where we got that row of zeros at the end of that equation of zeros. So you could say, in general, that if you have X, Y, Z, and W, that you could, if you think about putting everything in terms of W, that's 1/3 W, W, 1/3 W, and W. And so this is kind of, in fact, we've actually written down the solutions sort of systematically. I mean, it's really up here too, but okay, that's enough. I know that was very tedious, but hopefully you're getting the idea. And when I talk about the row reduction algorithm, hopefully this will seed all the ideas for you, and you'll be able to see how it works. So, okay, I need a drink of water. Thanks, guys. I'm going to stop the video.